All right, welcome everybody in the room, everybody online listening to this month's Space Telescope Science Institute public lecture. We really have a treat this month. These public lectures are usually on a cadence that follow around the early week of the month, but we have aligned this public lecture with a science meeting we are hosting here at the Space Telescope Science Institute. And so because of that, we have a lot of experts that happen to be in the room here that are going to ask wonderful questions for our presenters. And we also have a wonderful guest who I'll introduce in a few minutes, who will talk a bit about Nancy Grace Roman, the person, not just the space telescope. So again, STScI public lecture. Let me do a few housekeeping. So I am Brandon Lawton. I'm a scientist in the Office of Public Outreach here, and I lead our efforts for Roman science communications at Space Telescope. And I want to special thanks to our amazing tech team, Thomas Marufu and Grant Justice, who are in the back and making sure that this all runs smoothly so that people online can enjoy as well. Okay, just a plug of upcoming public lectures. Our next one will be on July 11th. The topic will be Stephan's Quintet, a multi-wavelength exploration. Our very own Frank Summers will give that presentation. In August, we have the topic for Webb Space Telescope, the first year of science. It's already been a year of science. So we're reaching the first anniversary of the first images from Webb. And so we'll have a wonderful presentation in August on the first year of science from Webb. And then on September 5th, we have a topic, Interstellar Medium, with the speaker Alexandra Hermanowicz from Space Telescope. So please join us for those. Also, you can connect with us. You can sign up at on our website, at Hubble site. You can subscribe to the YouTube channel. We have all of our previous public lectures there. And you can also submit comments and questions. And we have several social media channels to get involved depending on your interests. So, of course, we have social media channels aligned with Hubble's Telescope, Webb Telescope, NASA Roman, and the Space Telescope Science Institute. So you can find us in multiple places. Okay, so I wanted to just do a couple slides just to set the stage, and then our speakers are going to take it away. Okay, so first, we are here to talk about the Nancy Grace Roman Space Telescope and Nancy Grace Roman. So who was Nancy Grace Roman? She was NASA's first chief of astronomy. She joined NASA in the 1950s. When NASA as an agency was only a few months old. So she was in at the very early stages, and she is credited with shepherding essentially the astrophysics program and what became of the flagship astrophysics missions and other astrophysics missions at NASA. And so you'll hear more about Nancy Grace Roman in a few minutes, but that just sets the stage for who she was. And now the telescope, for those listening to the public lecture online, I want to set the stage for comparing this with Hubble and Webb in some ways. So one of the important things to think about for the science of the Nancy Grace Roman Space Telescope is that it is going to be very complementary and special in its own way and complementary with Webb and Hubble. And this is just one way in which we can show that. We have Hubble and Roman. You can see the mirrors, the light buckets that collect the photons from the universe. Hubble and Roman have same size mirrors. Webb has a larger size mirror, so it's very sensitive to collecting photons from faint objects in the universe, and in particular infrared sources, because it has a very thin layer of gold. And so Webb is very great at collecting photons from faint objects in the distant universe, or faint objects in the universe. But then you can see down here under wavelength, these missions are very complementary. Hubble is not going away anytime soon, and we certainly hope it keeps going for many, 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 many more years. And in particular, Hubble is our eye to the ultraviolet universe. We do not have another space telescope planned in the near term that will be able to do what Hubble can do. Hubble, of course, also observes through the visible spectrum and into the near-infrared. Roman is sort of in this little sweet spot here between visible and near IR, and then Webb goes way out into the infrared, into the mid-infrared. Okay, and so Webb has capabilities, again, that is provided by going into those larger wavelength regime. All right, so what Roman really brings to the table is that it's a survey space telescope. Roman will have Hubble-like resolution, Hubble-like quality data in the near infrared, but it will have about 200 times Hubble's infrared view of the universe. And so that's what we call its field of view. And so that's what you see in the upper right, is you see that funny shape there. That's the collected field of view of the 18 detectors on Roman's wide field instrument camera, and that's what it can see in one pointing. And here, for comparison, you can see what Hubble and Webb can see in one pointing. So really, Roman is going to be instrumental, pun intended, for building up maps of the universe at high resolution. It's going to be a much faster space telescope than Hubble and Webb. It will be able to take an image, move very quickly, take an image, move very quickly, and build up these really high resolution maps. And so these three observatories working together are really going to feed a lot of our understanding of astrophysics throughout the 2020s and into the 2030s. And so with that context, I just want to introduce our first speaker. So I want to introduce Dr. Joan Gordon. So Joan got her Ph.D. in 1982 from the Ohio State University in psychology, and she met Nancy Grace Roman through her aunt, who was a member in the American Association of University Women with Nancy, and Joan became a close friend of Nancy's later in life, in her later years. And after Nancy's death, Joan authored the press release for the Associated Press and co-produced the segment aired on Sunday Today with Willie Geist. Joan will be sharing a personal side of Nancy with you all. So, Joan?
Thank you. I just want to make sure everybody can hear. We're good? All right. So we're just getting, so I just only have a few slides to share to kind of like keep me on point so I don't drift into outer space, no pun intended. All right, thank you. And here, I know her, and please forgive me if I call her Nancy Grace. I'll try to say Dr. Roman as much as possible. But I know her as a family and as friend. We're not blood related, but we were so close. She was like a second mom for me. Oh, I need the clicker here. Let's see. Or if it's this way. Oh, there we go.
Try it one more time.
Okay. To the left or to the right?
To the,
usually to the right.
Yeah, to the right.
So I'm going to play a video that NASA produced. It's less than 7 minutes, but it talks about her entire life and some of her aspirations and all. And then from that, I'm going to share stories about Nancy Grace, Dr. Roman, with you, how I know her as a person.
Sorry.
It's okay.
We may need an IT 911.
So while they're doing that, let me just give you my background. So I did my work at The Ohio State University. I got my doctorate and my master's there in instructional television and in psychology and cultural anthropology. Fast forward, I spent a number of years in corporate America working for IBM, working for what was then Lucent Technologies, and then for the past 13 years, I've been in the military health system. Most of the time working at Walter Reed National Military Medical Center. So when they did the big merger between the Army, Walter Reed, and with the National Naval Medical Center, I had overall responsibility of training thousands of people who would either work at Walter Reed National Military Medical Center or go down to Fort Belvoir Community a hospital.
What lady would take mathematics instead of Latin?
We want to see the video. You don't need to hear about me.
What lady would take mathematics instead of Latin? The idea of Hubble was something that was among the astronomical community for generations. It was not something that was new. Astronomers badly wanted a large telescope above the atmosphere. Well, I decided that if the aerospace companies were going to put a lot of money into designing a telescope, they might as well design one that made sense. So what I did was to bring together a collection of astronomers from all over the country, trying to represent a variety of things that we might do with the telescope, and to bring in some NASA engineers and get them to sit down together and come up with something that the engineers thought would work and that the astronomers thought would do their job. Well, I think I've always been curious. I just wanted to satisfy my curiosity, and astronomy in particular was the subject I wanted to learn more about. I blamed my mother because she used to take me out and show me the constellations and show me the northern lights, things like that. I just was fascinated. Between 5th and 6th grade, I organized my friends into an astronomy club to study the constellations. And by 7th grade, I decided I wanted to be an astronomer, and I was going to try for it. I knew it was going to take me another 12 years of schooling, but I figured I'd try. And if I didn't make it, I probably could teach physics or math in high school. I certainly did not receive any encouragement. I was told from the beginning that women could not be scientists. In high school, one of the experiences I remember is I asked my guidance counselor for permission to take a 2nd year of algebra instead of a 5th year of Latin. And she looked down her nose at me and sneered, "What lady would take mathematics instead of Latin?" The first encouragement I got was in my junior year at college, when the head of the physics department came up to me in lab one day and said, "You know, I usually try to talk women out of going into physics, but I think maybe you might make it." My main astronomical research area when I started out was what they call spectral classification, looking at stars, spreading the light out into a rainbow so that you could see the different colors separately. What I started out doing was looking at these spectra, looking at these rainbows, and deciding the temperature and the brightness of the stars. And then I was trying to find out how far away they were and how they moved. My thesis professor was one I often didn't get the support that I'd expected. There was a period in which he went for 6 months without speaking to me, even when I said hello to him in the hall. He didn't want to have anything to do with me. I didn't think I could get tenure as a research astronomer. I didn't think I could stay, as they say, in the academic community, because I looked around and I think there was one other woman in astronomy who had tenure in this country, but I saw very senior women who didn't have it. When NASA came along and offered me a job, I decided to take it. I started in NASA in 1959. I was 6 months old. When I joined the government, I was hired as a fresh Ph.D. in spite of the fact that I had not only 6 years of experience, but an international reputation. And afterwards, I understood the reason. My salary at the university was so low that civil service did not recognize it as a professional experience. Being the first executive woman at NASA turned out not to be terribly eventful. I was accepted very readily as a scientist and as in my job. The men were very cooperative. And I felt that the men treated me as one of the team without a problem. Civil service had rewards for outstanding work. But they were limited to men. Someone decided that there should be something for women. In 1962, I received the Federal Women's Award. We all met with Kennedy in the course of receiving the award. I'm happy about the fact that women can get senior jobs now, and they're not being quite as discouraged as I was. But I think there are two things that I would like to see change. One is salaries. Salaries are still not equal. And the other thing is I'd like to see more uniform women across the ranks. Women can get into senior positions in astronomy now, but they're percentage-wise, they're still few at the high levels. It's hard to decide how history will view my accomplishments. People generally aren't terribly interested in what gets things started. And so I'm not sure they're going to have much of an idea of my role.
That's okay. Oh, great, thank you. So I thought that would do a much better job about Nancy Grace Roman and her career versus me going through what she had shared with me. I'll share some stories in relation to her career and personal things as well. So here I have it as she was family and friend, especially in the later lives, in her later life. I spent a lot of time with her because she and my aunt stayed in an independent living. She had her apartment, my aunt had hers. And so whenever I would visit, I had to visit both. Whenever we had dinner, we would have dinner together. We had dinner together for Thanksgiving and Christmas, year after year after year, when they dwelled in the same place. So I really got to know Nancy Grace then. I met her back in 2006. I had heard of her, but I met her then, and I would take her to some recognition programs or places where she was judging competitions, etc., in the sciences. And then I got to get to know her even much later. So I knew her through my aunt, and this is my aunt over here, and they met at the American Association of University Women back in the 70s. And they served on committees together. They created a memoir group, and so Dr. Roman, let me keep saying Dr. Roman, had some memoirs that I don't know where they are right now, but she wrote a lot of things about her life. I know that she was working with somebody who was going to do a biography of her. But has anyone heard anything about that? I didn't get her name. I remember her telling me that. So they met there, and I used to go to the meetings with them or take them to the meetings, more of that, and so I got a chance to know her even better. And another thing was Exploravision, and that was a competition for kids, like middle school through high school, between Toshiba and the National Science Teaching Association. She was one of the judges, and these kids would come up with solutions, scientific solutions to problems. And what was really neat in going here is that, because that started in '92, you would hear from graduates who have gone on to medicine or anything else and how it started there. And then they did a lot of sayings in terms of what Nancy Grace had inspired them. So usually after these sessions, she was always surrounded by kids, and they wanted her autograph or they had questions of her. This was one of the things she was really proud of with the Legos. And so I told her, I said, well, I know that she's very interested in setting up funding for women who wanted to pursue the sciences. And so I recommended, I said, well, listen, from the sale of this, maybe a proceed of that can go toward it. I don't know if that really happened, but she was really, really excited and honored to have had something like this. Now I'm just going to talk about her as the person. Tenacious, resilient, and a trailblazer. So she was tenacious. I remember her telling me how she knew she wasn't going to get tenure. And so it was like, okay, so what am I going to do? And then she met someone who said that he was looking for somebody to work at NASA within the next 6 months. And then she was hired. Tenacious from a personal side. It was very cold. Let's see, maybe it was back in 2016. And we were concerned that she needed a new winter coat. So I went out to get her a coat. Took me a long time to find this coat because I wanted to get one. Let me do this way. I wanted to get one so that it gathered and the cold wouldn't go, in. And I tried on all these coats. All excited about it. I called her down to my aunt's apartment and I said, I have something for you. And so I bought a hat, scarf, and matching gloves with it. And I said, well, listen, I think this can really help you. You should take this. Oh, no, I can't take this. Oh, no, I already have a winter coat. I don't need this. I said, if you would just please try it on for me. I spent a long time trying to get this coat. And then she put it on and she said, no one's ever done anything like this for me. But she wouldn't take it. And I think the reason why, I was really, really upset. But I couldn't show it that much. But anyway, because we both were like, you're going to take this coat. No, I'm not. You're going to take it. No, I'm not. And so I think she really didn't want to take advantage of my quote unquote kindness. And I said, but we're family and I'm doing this for you. Don't worry about it. I said, I don't want you to pay for it or anything. I just want to make sure that you're warm. Because she used to take that shuttle and go everywhere, shopping, to the Kennedy Center, and I just wanted her warm. She won that one. So I said, okay, yeah, she's tenacious. There was another incident where her lamp wasn't working. So I said, oh, well, I'm going to go get, either we can go on Amazon, but I think I'm just going to go and get you a new lamp. And she said, you will not get me a lamp. We are going to fix this lamp. We're going to repair this lamp, and you're going to help me. And then she said, my father raised me to be independent, and my father taught me and her father was a scientist. He taught me how to fix a lamp, and I'm going to teach you. So she wrote everything out that I had to go to the local hardware store, not Home Depot or any, no, I had to go to the local hardware store, and I got whatever she needed. And we sat at her dining room table with this lamp, and we replaced the wiring to it, and she taught me how to do that. She was extremely proud, but in a humble way, but very resourceful. So that was one of the things. So I said, okay, I'm glad that I learned how to do that. When I would visit, now we have grocery stores, right? She thought her refrigerator was a grocery store for me. And so she would go to her refrigerator. She called me Joni, not Joan, but Joni. Here, take this. Here, I got extra this, and blah, 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 blah. I think you should have this. Take this home with you. And I want to say, do I look like I'm not eating, or what's the problem? So what I did with her, I said, okay, because I used to do some of the shopping if she wasn't able to do it. I realized, let me just shop just enough for her, not get a whole lot that she would want to share with me. So I said that fixed that problem. I was the one that helped her with her computer, if she had problems with the printer, and she wouldn't, and maybe I shouldn't say this, but sometimes she would share some of the NASA things with me, and I was totally amazed. Now, it wasn't confidential, okay? It wasn't confidential. I don't want to get arrested or anything like that. But I was totally, she's telling me certain things, and even on the tour today, it reminded me of the things she shared with me. And I was just like, I kind of like tuned her out because I was so amazed with what I was seeing. I said, oh my goodness, this is amazing. And she's like, yeah, okay, we're used to it. And so I used to go up and spend hours, which would make my aunt a little bit jealous because I was spending so much time up there. I was learning. I was like a sponge with this stuff. She had a special cabinet with all of her slides. I mean, thousands of slides. So I'm hoping that NASA has some of them because I know she would want NASA to have them. Whenever she got ill, she called me, or they would call me up, and I would go to the hospital. And so, like if she's in the ER or the ICU, usually those places are limited to family. So I would show up, and they would say, oh, your mom is in cubicle such and so and so. And I said, well, I didn't think I looked like Nancy Grace, but that's okay. She would not correct them, okay? And so I remember going into the ER. For whatever reason, they were trying to get her ready for an MRI. She wouldn't drink the water. So I walk in there, and it's close to midnight, and the woman said, oh, I'm so glad you're here. Maybe you can get her to drink some water. And so I grabbed the water, and I said, now you know you need this water. You know you need this so that we can go through, the next phase of whatever we're trying to do. And she would drink it. I said, even if it's just a little bit at a time. So she would drink it for me. So people got to the point, like, if you need Nancy Grace to do something, get her daughter. She'll come in and make sure she'll do it. She'll make her do it. There was one thing when we moved her from the ER to a bed. They found one. This was over at Holy Cross Hospital. And so I told some of the nurses about her background. And they said, oh, really? Oh, and I said, well, she was a trailblazer, really, for women in the sciences. These nurses, about 6 to 8 of them, came into her room at 1 in the morning. Yes, I was still there, of course, talking. And they surrounded her bed, and each one said thank you to her for the contributions she's made, and they clapped for her. And, it was absolutely wonderful. And she just sat there and she smiled. And somebody said something about, well, your mother this, that, and the other. She never corrected them. She just sat there and felt like, yeah, that's my daughter over there. So I've had, just a wonderful time with her. I didn't know her from the science part until we would look at the stuff on NASA. I know if she were my mother, that I probably would have gone into astronomy because I was so, enamored with everything that was going on. When I was 6 years old, I actually built a model of the universe. So at that time, by memory, I had done that. So even back then, I guess maybe God knew, okay, later on you're going to meet somebody who can help you with that. But she was resilient. She would always bounce back health-wise. And then again, a trailblazer. So for me, not to say too much, or I could just, like I said, This is one, and I really love this quote from her. And it says, I was told by many people that a woman could not be an astronomer. I'm glad I ignored them. And that was out of recognition back in 2016, and I was there. So I'm glad that she ignored them. I feel very blessed that she was part of my life and I was part of her life. And there are many other stories, but I'm not going to bore you with them. But she was a true delight, sense of humor, and so I knew her from a different perspective. So that's my talk. I don't know if people have questions or just, I know our time is limited.
Go ahead and keep that on. Well, let's take some questions. We have time for questions.
Yes.
And do we have is there a mic that we can pass around?
I'll just repeat it.
Is it here? You want to repeat it? Okay. Okay. I'll just we can repeat it here. Go ahead.
Thank you for your talk.
Did
Dr. Roman ever have any inkling that there might be a telescope named after her someday?
No.
So the question, sorry, the question
sorry.
was, did Nancy Grace Roman ever have an inkling that a telescope would be named after her someday?
To my knowledge, no, she never, we only talked about the Hubble. And she really didn't like being called the Mother of Hubble, but she got used to it. But yeah, that was it. She would just be, golly, I don't know, so elated if she knew something like that. And maybe she does in the heavens, she knows about it, but no, Yes?
So I'll confess I'm going to do the Nancy Grace Roman hand for us. I've even got the shirt.
Okay,
Check,
I
check.
love this shirt.
Thank you. Your sunglasses stay in focus. But so part of looking into her life, this may not be relevant, but I'd see all these pictures of her wearing pearl necklaces, and so in one hand I totally get. I mean, she was a force of nature in what she accomplished, but I get the impression she kind of had a kind and gentle side too. I was wondering if you had more you could say about that.
Very, very much so. She wanted to establish some type of fellowship or scholarship for women in particular, not to ignore the men, but for women in particular. And then when we would go to these recognition programs and the young people were there and they're surrounding her, she always took the time to speak with them. We were literally like the last people to leave unless she was tired. She spoke to everybody. She poured herself into her work, but she also poured herself into people. And I think I became a recipient later in life. So I went through a period where, with my job and with certain challenges, and you deal with people who may be envious of your abilities and things like that, and I'm sure she did as well. So she would share her pearls of wisdom with me. Well, this is what you need to do. And we would speak for hours about that. And she didn't have to do that, but she would do things along those lines. So a very giving nature. I have her mother was a classical pianist and a piano teacher. So she gave me her mother's piano books that are like 100 years old. She wanted to give me her mother's baby grand. It was a Steinway, but it wouldn't fit into my place, which really made her upset. But that's how much, my aunt would say that's how much she thought of me. Her mother was also an artist, and so I noticed in her other place where she used to live, all of this artwork. I said, well, this is incredible artwork. Who's the artist? My mother. So she took care of her mother when her mother became ill, I think maybe back in the 90s. So she, just that kind of person, the person who was the aide for her mother, they were friends for years. And so she included that person as family, and that person had children, so she looked at those kids as grandkids. So anything that they needed and she could help, she did it. So it wasn't anything where she had to announce it, she just did it. And you can find out, or if you didn't, it was okay for her. She wasn't a showy person, so that just wasn't her thing. And in terms of constantly being in the spotlight, she did a lot of traveling globally, and so that's why I was looking at all these slides and said, oh my goodness. She did talk about getting the financing for the Hubble and how she had to prepare briefing after briefing after briefing to get enough money for it. And she finally was successful in doing it. And she realized it was a team effort as well. It wasn't just Dr. Roman. So she always would give credit where credit was due. So I think, yes. Mm-hmm.
Thank you. And I really enjoy getting to hear about all the stories from Nancy Grace Roman, and I wonder if you might be able to help me with another story.
Okay.
Of course, she accomplished so much during her long career, ranging from being like the first scientist to go beyond the Iron Curtain, all the way to founding the building that we're sitting in right now. But based on her recollections, what did she focus on? What was it that she really felt she was most proud of in life?
She was very proud of her parents, and especially her father, both of them. So she spoke very highly of them. Also, she was an avid swimmer. Did you know that? She loved to swim. And so at the last place where she stayed, she did a lot of that. We were concerned to make sure she didn't catch cold, but she was fine. I think for her is not just the work, not just the telescope, but being able to pave the way for women. That was huge for her, because she knew when she was at the University of Chicago that she wasn't going to get tenure. And in fact, and maybe I shouldn't say this, but in fact, she said they insinuated that she really needed to go somewhere, settle down, and have a family. And so that was how she was treated. And she was wrestling with, okay, so what do I do next, okay? So after she went through that, she really wanted to make sure that other women behind her would not have the same experiences. So I think that's part of her legacy. That was her passion. And in her memoirs and all that she's written, that's central to it. But she's open to help anybody, so it's not just, well, it has to only be women or young girls or whatever. Thank you. I hope I answered it. Are there any other questions? I don't want to take up your time because I know we have another presenter. You have been fabulous. This has been such an honor for me. Yes, sir. Oh, did you? Oh, I thought, oh. Oh.
Oh, did you have a question? Did someone have a?
I heard
I
somebody.
wanted to ask do we have any questions from our online community? I don't know what the hand signals mean. Oh, we'll do that at the end. Okay.
Okay.
Okay, so we can take a few questions at the end from the online community. Any other questions? Well, we have Joan here. Yeah.
Maybe you can tell me if this is a true story. I heard that in her later years, Dr. Roman used to sit in meetings and knit, and she would seem like she wasn't paying attention, and then she'd put down her knitting and say something absolutely astonishing. Are you familiar with that story?
I'm not familiar with that story. I think with her hands, it was hard for her to do knitting, but she was really perceptive. I mean, you can say something and you really thought she wasn't paying any attention. Oh, she paid attention and could repeat it. So we've had that experience. She also liked to sew, so I'd have to go to her place and thread the needle for her because of her eyesight. It was hard for her to see it. But yet, once got everything set up, she could do that. But I had heard that today, and I wasn't sure, but I'm sure she did that in a way. Well, she always had to be doing something. She was always busy. And sometimes when you do things like that, people think, oh, she's not paying any attention. We're just going to say this, and we're going to do this, and we're going to do that. And then they get caught. Because then she can repeat what, you thought I was very busy with this, I am, but I'm hearing everything. So that probably was true. Yeah, definitely true. Knowing her, she just, it was just like, she had to be on the go. That's why I wanted to give her that winter coat, because I knew she was going all over the place.
Hi, so I have a question about the Hubble Space Telescope. So I know there's obviously a lot of people in this room that Hubble has shaped their careers in terms of astronomy. So I was wondering if you could say anything about whether she mentioned what was kind of the key to getting Hubble off the ground for her personally.
For her, the key thing was funding. Making sure, first of all, making sure she had the right team to manage. And as she said, when she joined NASA, people thought, oh, it's going to be real exciting, but it wasn't like, oh, you're the first female and all of it. She got over that. But for her, she wanted to be surrounded by people who were smarter than her and then who could get the job done in time, within schedule, and within budget, preferably less, under budget. That was her thing. So for her, it was like, again, going before, and she told me how often she had to go before Congress or somebody else had to, in order to make sure they had the appropriate funding for it. But yeah, she just said, and she used to tell me, you want to make sure, you're managing people, which I've done, get folks who are smarter than you, and they'll make you look good. And recognize people, even just saying a mere thank you to somebody is wonderful versus just, the other stuff. But she was very, very good at doing that.
Any other question?
I'm going to be around, if that's okay. So
Oh,
if
yeah.
somebody says, hey, I really wanted to ask this, but not in public. Oh, you had your hand up? Yeah.
I said this during the other talks we were having, and when I first started working here in July 1985, there were a few times I sat next to her in meetings here, not knowing what her role was or who she was. I was just new, didn't know anything. She talked to me very graciously, and I was telling her what I was working on, what part of things, and she was asking me other things. And she just struck me as a very gracious, nice person. But in the course of sitting there and listening to other people and the questions she would ask people then and things like that, it dawned on me, oh, this is a really important person that I sat next to.
Oh, my goodness.
So it was just kind of a, wander in, sit next to somebody in here in the auditorium you don't know, you're new.
Well, we did. I had to take her, my aunt, and other friends from the independent living environment to a wake. And so there were some young men at the wake. And as we were leaving, I told them, I said, oh, well, this is Dr. Roman. She created, the Hubble telescope. And Nancy Grace was walking away. They were running after her, running. And these were guys probably in their 20s. They said, oh, wow, oh, cool, really? And I said, oh, yeah, she did that. And I don't know, I just shared that in passing. And they ran after her. They, of course, held us up, so we couldn't leave right away because they had questions of her. But that's just, who she was. So it wasn't like, okay, well, Joni, we got to go now, No, she took the time to talk with them. So there are so many other stories about her, but again, I was blessed to have known her. She touched my life in different ways, and hopefully I touched her life in different ways as well, even though she didn't take that coat. Yes, I have not gotten over that. In fact, I gave the coat to my aunt, and I went and got the same coat myself. Because then I said, well, maybe she'll look at it and say, that's a nice coat. Yes, it's yours. Take it. So, but anyway, I was with her 2 days before she passed away, and I told the nursing staff, I said, she loves the classics. So please play the classic music on the television, on one of those channels for her, and they did. She said that, oh, I have a taste for strawberry ice cream. I said, we'll get it. So please give her some strawberry ice cream. And they said, well, you can spend the night here. We'll get a futon for you, and you can spend the night here. I said, no, I'll come back, and I'll spend Christmas Day with her. Well, unfortunately, that didn't happen. I got the call around 2 in the morning that she had gone away. So, but at least I was able to spend some time with her, and that she knew that she was loved by family local, as well as she has 2 cousins that she spoke very highly of, and then another cousin who was in Texas. So she really said a lot about them. But as far as local, she didn't have immediate blood family, but she had us. So anyway, I'm going to hang around afterward if that's okay.
Absolutely. Yeah.
I mean, if you're doing something confidential, I'm
No.
I'm out of here. But I don't mind staying. So if somebody wants to ask me something afterwards, off record.
Yes, let's thank Dr. Gordon again.
Thank you. I hope I didn't ramble too much.
No, it was wonderful. Okay, so I have the pleasure, of course, of introducing our second speaker, who's standing here next to me. So Dr. Rachael Beaton joined the Roman Telescope branch here at the Space Telescope Science Institute in 2022. Prior to this, she was a Carnegie Princeton Fellow and a Hubble Fellow at Princeton University, and a postdoctoral research associate at the observatories of the Carnegie Institution for Science, after receiving her Ph.D. in 2014 from the University of Virginia. So Rachel will discuss the Roman Space Telescope mission and how it will achieve breakthrough science. Rachel?
Oh, it needs to be green.
Okay, cool. All right, I have to swap the slides really quick. This is actually one of my big jobs this week at the conference. Awesome. And okay, so I'm going to talk about Nancy Grace Roman, and I'm going to use things that she said, and then use that to introduce the Nancy Grace Roman Space Telescope, because I think this mission is particularly emblematic of the person we just had so vividly painted for us, for some really specific reasons, not just the science, but how the mission is going to work and who the mission will reach in terms of scientists. And I'm glad Joan mentioned what she did, because the best books that I found about Nancy were these two kids' books. There's a beautiful Trailblazer bio about Nancy, and then there's also this really beautifully illustrated book about Nancy. There's not a biography about her. So I read oral histories, and I read conference documents and decisions to actually find out what she thought and the kinds of things she went through. So if anyone's listening that wants to write something more adult, but not quite a committee report about Nancy, let's chat, because I have about 800 tabs open right now, and I'd like to put them to good use. So one thing that Nancy said is she said, when NASA was formed, one of the men there asked me if I knew anyone who would like to set up a program in space astronomy. He didn't ask her, he asked her if she knew anyone. And so she applied. So she says, and I decided that the idea of influencing astronomy for 50 years was just more than I could resist, and so I took the job. So at this time, Nancy was working at the Naval Research Labs. She only worked there for a few years. She had moved there from Yerkes Observatory at the University of Chicago, where she had been teaching after getting her doctorate. And after teaching for several years, in the video we heard she didn't feel like she was going to get tenure. It wasn't exactly a feeling. She actually went to Chandrasekhar, who is a very famous astronomer, and she complained about her salary. Like they mentioned, the civil servants didn't consider her salary high enough to count as technical work to get her into a higher level. And she complained about it, and he said, well, because you're a woman, I can pay you less. You're cheaper. Okay. And so she said, fine, I don't have to work here anymore. And she moved to the Naval Research Lab. And so when she said she felt like she wasn't going to get tenure, it was made very clear she wasn't going to get tenure. But she went on, I think, to do some of the most transformational things that probably could have happened to astronomy as a field. There's a great quote at the end of an article about her. It's actually from Twitter. Twitter's supposed to be backed up some way, but I don't know, Twitter's had a bit of a tumultuous year, so I couldn't find some of these old tweets, but I really love this. This was in a celebration during the renaming of this mission. She said, Nancy Roman took chief astronomer job at NASA because women couldn't get tenure, opted to reshape the history of astronomy and said, #Plan B. So, from that kind of defeat can come some really true greatness. So, one thing that Nancy says is the real way to learn about the night sky is to look at it. So I recently gave a talk about the Roman mission and about Nancy in front of a bunch of kids. So I thought this was a really great way to get them thinking about the night sky. We were also outside in a national park, so we really wanted to think up. But why I wanted to use this quote to talk about Roman has to do with its field of view and how that's unique. So this is a kind of real picture. So this is a real picture of the horizon. So if you went outside, the horizon's here. You can see some light pollution off in the distance. And this is a real picture of the moon. That's how big the moon is on the sky. And this is actually a UV image of the Andromeda galaxy, but it's not what you would see with your eyes. It's if you could see this thing with your eyes on the sky. That's how big the Andromeda galaxy is on the sky proper, which is cool. I actually used to study its halo, which goes way out, which is always a fun thing to show. So I want to put this picture in context with the Roman field of view. So this is the same galaxy, it's just rotated differently. I had a different view where I actually rotated it, but this one has words, and I thought that might be confusing. But there's the moon to scale. And so the Roman footprint is an appreciable part of the night sky. So one thing that's really hard to talk about Hubble with the public is that those images are so tiny. So the Hubble images are about the width of my ring at arm's length on the sky. Tiny little patch of sky. Your Roman field of view is about the width of your thumb on the night sky held at arm's length. So if we were outside, it'd be a lot better demonstration, but just keep that in mind. Like a Roman pointing is something that you can go outside with your eyes, with the instrument that astronomers used, that humans have used for what, 20,000 years to observe the night sky, and Roman will be looking at something like that, which is pretty cool. But in getting this huge field of view, we're actually not sacrificing the detail. Okay. Hubble is amazing. It has inspired people for 30 years because of the detail and the beauty. So if I swap to actually looking at these in the background are real observations taken from Hubble, but mapped onto the Roman field of view. To give you a sense, we have this huge field of view, this thumbprint at arm's length, but I can zoom in and see with incredible detail, with Hubble level detail, a ring's width on the sky. Okay. And in there is embedded all the beautiful astrophysics that gets us from the primordial soup at the beginning of the universe all the way to the life here on Earth. So we have young stellar associations, dust clouds, and associations of stars. So we're not just getting this huge field of view, we're getting all the detail at the same time. Now, this huge field of view, taking one picture, gives us an ability to actually map huge areas of the sky. So if we take everything that Hubble has ever observed on the sky and we put it all together and tried to observe it with Roman, which you can't do because it's all over the sky, so you put it all together, we could do that in about 60 pictures. But we don't want to brag and make Hubble feel bad because Hubble has done some really amazing work. So the way to think about this, and why I wanted to start with this, the quote to look up, is that this blue, hopefully you can see it, it's this double-lined box, is actually a footprint that was considered for what is called the high latitude, oh gosh, am I going to blank on the name of the survey? Wide area survey, thank you. See, teamwork. And I've placed it to scale on a plot showing you the constellations over the full sky. And I've picked out a few in particular that are quite important. There's the summer triangle, which is quite famous. So were it not raining, on your way home, you could look up and see these bright stars on the sky. Roman's survey will cover that whole area around it. So, wow. And we're going to zoom in just like a Hubble image. Okay. Another pretty famous thing is actually the winter hexagon. So those teachers in the room, you can actually use this graphic summer or winter. We will map almost the entirety of the winter hexagon. So we're probably not going to do this patch of sky. That's being debated right now, what patch of sky we'll do. But that's just a tremendous amount of sky. And my favorite one is we'll actually map larger than the area of Ursa Major, which contains the Big Dipper. So that's also something you can go look at. It's actually my earrings. That's how big the wide area survey is. So it's about 2,000 square degrees. And for the astronomers in the room who like data, this is from Wikipedia, the actual area of all the constellations sorted by area. And the largest constellation on the sky is about 1,300 square degrees. So our wide area survey will be larger than any one constellation. Okay. Cool fact to take home to mom and dad. That's a fun one. It's not only that we have this area, it's that Roman can actually do things very quickly. So I did some back of the envelope math, and to cover this one time is about 7,200 pointings. The equivalent with HST would be about 660,000 HST pointings, and this is 100 times more area than Hubble has observed over 30 years. So in a couple of years, you can actually go outside and look up, and then you can pull out your phone and you can zoom in to Hubble level resolution. Okay. Let me give you a real simulated data. This is a simulation that was done by my colleague Sebastian here at the Science Operations Center. So this is real data that's then simulated through something that simulates what Roman's going to do of the Hercules star cluster. This is a cluster you could go out and observe with binoculars or a small telescope. And that is the Hubble image up there, which is just of this tiny little region. And so we get all of this area at one go. But to just really drive the point home, I'm going to zoom in on that one chip, and we get all of this beautiful detail as well. So fun times ahead. The other thing to keep in mind is that I'm talking a lot about things in the nearby universe, constellations, star clusters, and this huge area. But actually, as we look further and further away, we're looking back in time, and this large area to us nearby actually gets bigger and bigger and bigger as we look further and further back. So not only do we observe what's nearby, could we observe the Big Dipper, we actually look all the way back and in our deep surveys and get these huge areas of the sky in older times. And that is going to be tremendous for doing cosmology, for studying the evolution of the universe at these large scales. So on the largest scales, the universe is very homogeneous. It's boring. But you can get unlucky and study a patch that is more or less interesting. So this survey is going to give us these huge areas where we can average over and get a really good understanding of what's going on. In our writers' workshop that we had as part of this conference, someone compared it to taking little tiny snapshots of a scene and looking at them individually versus seeing the whole scene at one time. We're going to start getting the whole scene. We have a different survey that's not going to cover a huge area. It's going to go to the same area and view it many, many times over the course of the mission to see what changes. And some of those things that change are called supernovae. And supernovae are cool because they're so bright. They're brighter than an individual galaxy that we can observe them. So they're individual stars or maybe binaries, depends on who you talk to, that are exploding, but we can see them all the way back to half the age of the universe already, and we might be able to see them further. People are working on it. And that's incredible because these things are standard candles, which means we know how bright they should be. They're standards. So we actually can measure distances all the way out to half the age of the universe and measure how the universe changes in a very simple form. There's people here at this conference that could tell you all the details, but that is for another day. Okay. Another thing I wanted to talk about with Nancy is she has this quote that was used to try and convince people to do a space telescope. And she says, looking at stars through the atmosphere is not too different from looking at streetlights through a plane of old stained glass. Okay, so just imagine that in your head. So the atmosphere is like 1,000 little lenses bending and moving around, and it causes the image that's made on the telescope plane to bounce around and get blurred. And this is why we do space astronomy, because we're going to put our telescope above the atmosphere and just skip that whole atmosphere step. So when she started talking about the idea of a space telescope, believe it or not, most astronomers were like, no, not for me, not what I wanted. So a tremendous amount of her work was convincing the community that they did want this. The engineers got so excited, and this flashed through in that talk, and it took me forever to find an actual copy of it. It flashed through in the video. The engineers thought this was rad. They're like, this is cool. So we're going to build this telescope, and then we're going to have this camera back here, and this astronaut will go up, and so that thing in his hand is a canister of film that he'll change, and then he'll take it back down to Earth, and we'll have all these pictures of space, and it'll be great. And Nancy, much to her credit, was just kind of like, yeah, that's a concept. I see you made drawings. Much to her credit, she then negotiated. It was a yes, but conversation. And there's a quote of hers where she says, I didn't know how to tell them we hadn't been using film in that way for decades. But you have to remember, it's 1969, and what's going on then? It's putting crewed space missions, putting orbital science platforms into space. So they were running with the theme, and they ran a little too far. But this actually gets a lot to the technology that you needed to have a space mission. So I talked about the atmosphere and how that adds all this blurring. And that means that we don't actually get to the physical optical limit of what a telescope can do. It's not until you get above the atmosphere. So having a human there meant you could only go so far up because you needed to go back and forth to take the film to CBS and get it processed. It also meant you had to have breathable atmosphere in the back and all through, and you had that heat, that extra heat of the humans and of the taxi, the Uber taking him back and forth. I don't know. There's lots of reasons why this is not actually a step forward for getting to that physical resolution, that beautiful, beautiful resolution. There was also a long debate about the camera that would go back there, because you want it to be not film, obviously, but you want it to be a digital camera, and I'll talk about, or something digital, and that technology wasn't in place in 1969 either. So there's a lot of talk about how Nancy slowed this process because she didn't feel like the technology was ready, but the technology wasn't ready, right? I mean, this was the concept of the technology at the time. So today with the Roman mission, we're even getting beyond the Earth. So this is a map, and this line here, this sort of dark kind of cyany line, is a representation of the Earth's orbit around the sun that's at the center. And what you're seeing here is a representation of the gravitational field that's much like a contour map. So where there's more lines together, you're stronger, and where there's fewer lines, it's weaker in this visualization. So the Hubble Space Telescope actually orbits the Earth. And what happens if you orbit the Earth? You spend half the time on the back side and half the time on the front side. And what that means when you're on the back side is you're shielded from the sun's radiation, and you can be quite cool. But when you're on the front side, you're getting heated up by the sun. Now, if we don't want an astronomer sitting in our telescope, we probably don't want the sun heating up our telescope. So in part of my science life, I measure something called the Hubble constant, and in my data, I can see the effect of heating up that telescope, and warm things expand and stretch out, and cool things cool back down. And I have to take that effect out to do my science. So where we're putting telescopes now, especially infrared sensitive telescopes, is out here at a point called L2. These are called Lagrange points because you solve the Lagrange equations and you get these 5 points where you could potentially send something into orbit. This is where James Webb is. This is where a satellite called Gaia is. And this is where we're going to put Roman. So we're getting far away from the Earth. We're almost always going to, and these points orbit with the Earth. So you'll always be in the shadow, and that gives us much more time to use this telescope. It makes it much more efficient, and it's going to be temperature controlled. And that gives us pointing stability, that gives us stability of the images that we're making, and it's fantastic. It also means that on occasion, we'll get some pictures of James Webb, maybe. There's a fun game that you have to play with web data and with some other projects where you're like taking out, people have rediscovered these telescopes out at L2 many times. So that will also be fun. So we're taking this concept a whole new level, getting as far away as possible, making this telescope as stable as possible to do that tremendous science. This mission actually ends up being less expensive than it could be because we're actually using a leftover telescope that came from the National Reconnaissance Office. And I'll leave the context clues about what the National Reconnaissance Office does. This telescope used to point down instead of out. So we got this frame and we're able to use it. They actually took the mirror that was in the telescope, refurbished it, polished it, fixed its surface to an extreme degree. And we're adding cutting edge technology to this telescope to let it do this amazing science. And one of the things that we're doing is we're making a camera that I just don't even know how to explain how awesome this camera is. We all walk around with a detector right now in our phone, several of them. And that detector is there. It's like your cell phone camera. This is one of the 18 detectors going into Roman. It's about the size of a saltine cracker. The folks in the communications at Goddard told me that was the official term. It's a lowercase s because we don't have the trademark. But that is a saltine cracker, and this is Greg, one of the engineers, astronomer engineers who works on it, just so you get a sense for the scale of this thing. And each one is about 12 megapixels. And this is based on ground data, but each raw set of reads that we get, which I'm not going to explain exactly what I mean by that, is about 12 gigs. When we put all 18 together, you get a detector array that you know is like something you can see and have heft. So that's a real person in their head and their hand. So you get a sense for that scale. It's kind of unreal, this detector. It is 302 megapixels. Each image is about 40 gigabytes coming off raw. Astronomers call it data processing reducing because we actually reduce that total volume down quite a bit as we process the raw data. But that's just a sense of the technology that we have for this mission and what is giving us the power to map constellations on the sky. This is a quote from Nancy after she retired from NASA. She retired in about 1979. She handpicked her successor, who called himself the first male head of NASA astrophysics. He's the one that really coined that term, Mother of Hubble. She retired to take care of her mother, and after a few years, she decided she wanted to work part-time. So she went to the Goddard Astronomical Data Center, and she sat down, and I hope the whole story we just had about Nancy, you can just see this conversation. She said, "Look, I know astronomical catalogs. If you'll teach me computers, I'd like to work for you." So she did astronomy on these measuring devices with pen and paper, calculated on a hand calculator, then was an administrator. So she had to learn how to use computers, how to use that kind of data to work there. She was hired at Goddard at the Astronomical Data Center. In a few years, she was actually the director of that center. And she worked part-time and telecommuted. This was in the 80s. She telecommuted so she could take care of her mother. And there's a whole section about how she's like, I kind of invented it. I feel like she might have forced it. But anyway, she like invented the concept. And over time, more and more people actually wanted to telecommute. So coming out of COVID, and as we're all adapting to working hybrid, just like Nancy was doing this in 1980. So we can do it too. So the thing I want to say is I've just talked to you about all that data, the 300 megapixels, the 40 gigabyte files. We have to learn as a community how to use this data, and it's a different context. I can't download that to my computer and do my analysis. I have to learn to do things in a new way. Let's put this into context. This is the data sent to Earth per day. HST sends about 2.7 gigs per day. So you need quite the hefty cellular data plan, but it's not out of context, right? JWST, 58 gigabytes per day. That's a pretty heavy data plan. Romans is going to send 1.4 terabytes of data per day. Yikes. That's a lot. When I say sending the data back to Earth, what I mean is on the spacecraft, the data are prepared and staged, and then they're sent to the Deep Space Network, which are these huge radio dishes across the world, where these dishes receive that data and transfer it here, or will transfer it here to Space Telescope for processing. Cool fact. You can actually go online and see what the Deep Space Network is doing at any given time, and they're going to get so busy when we start actually having Roman data. So, cool. But what does that mean integrated over time? All of the HST data taken for 30 years is about 172 terabytes. You could probably go to some sales online and get yourself 172 terabytes of disk space, even as a single human being with spare time and disposable income. But when we think about the JWST 5-year mission, we're talking about 1 petabyte, 1,000 terabytes. That's sort of out of scale for even a small astronomical department. It's definitely out of scale for an individual or an individual research group. Roman's 5-year mission will produce 20,000 terabytes, 20 petabytes of data. That is not data that everyone is going to look at. So for HST and JWST, a human looks at every image to make sure it's okay. For Roman, my colleague John, who might be here, he might have gone home, is actually devising how do we use machine learning to actually tell us the images that look good and look bad. It's so cool. But that's a sense for what our archive is going to be for the Roman data and why we have to transform the way we do science. We have to do it in a more community-driven fashion. We have to share resources, and this is going to transform astronomy. Just the ground testing data that I spend time thinking about is about twice this JWST 5-year mission. Yeah. I'm like, oh, I get to manage a JWST-sized data chunk for our ground testing. Cool. That's definitely on my resume. But anyway, just think about that over time. It's huge. Okay. If I brought anything to the Hubble project, it was perseverance and belief that it was possible. How humble is that? She testified for NASA. She got an entire astronomical community at a time when all astronomers didn't really get along to go behind this mission, formed the committee. She invented the type of NASA peer review. She was the peer review for a really long time, and then she started outsourcing it. She did all of this to bring Hubble around. It was greenlit for funding about 1978, about a year before she retired. It's more than just perseverance and belief. It's being incredibly effective and personable and going all across the country to convince astronomers to do this mission. If I had to pick something that Roman's going to do that requires perseverance and belief, it's got to be the coronagraph, which I haven't talked about. Fun fact, in 1959, the year she took the job with NASA, Nancy Grace Roman presented a paper called Planets of Other Suns, and where she describes what it would take to observe Venus, Earth, and Saturn at their maximum brightness and separations around Alpha Centauri, which is a nearby star. So cool. This is actually cited in the 2023 JWST early release science paper, but otherwise hasn't gotten a lot of citations. But this is how ahead of the curve she was in thinking about this kind of stuff. So what is the coronagraph? Coronagraph is a bit of magic. It's technology so advanced that it's pretty close to magic. that allows you to see Earths around distant stars. Not too distant, very nearby stars, but pretty far away. And this is an image of a bright star if you simulated like you were trying to look at it with a space telescope. The planet, the Earth-like planet, would be 10 billion times fainter than the star. I hate to disappoint you, but we're not going to be imaging Earths with the Roman coronagraph. We'll probably be imaging things that are a little bit brighter, like Saturn, Uranus, Jupiter, but we're going to be able to image them. So these things are more like, just casually like 10 million to 100 million times fainter than their host star. Just 10 to the 7. But the way we do this is with this fancy technology called a coronagraph. And so imagine here, this is our super bright star, and this is the light that we're collecting from it. And it's going to go to this first mirror and then into some lenses. So the actual image of that point-like star has this wavy pattern because of how optics work and Fourier transforms. We don't have time for that, but just trust me. How are we going to dim this by 10 to 100 million times? That was a duplicate slide. So let's zoom in. We're going to blow out the contrast here so we can see that pattern. It's called an Airy pattern. And here are 2 lenses that are going to do a lot of the magic. The first thing we do is we slide in this occulting device, which is basically going to take the light from the center, and it's going to spread it out to the outside where we block it. And that gets rid of a lot of the central obscuration. But if you note, I still don't see a planet there. So that's not enough. The next thing that we do, okay, and so this is the effective image. Once we put the blocker in, that's the effective image. You're still not seeing a planet, but you've gotten rid of all those airy patterns. I added a step there. So let's blow up the contrast again and look at that pattern. That pattern is fuzzy because the mirror here isn't perfectly matching what the optics, the telescope, is doing to the beam of light. And the beam of light is only so stable because of the pointing in other systems. And so that is the impact there. It's this just, ugh, ugh. So what we do is you actually take this mirror and you deform it until it matches the incoming pattern. And when you do that, or when magic people do that, these wonderful scientists that work on this, you all of a sudden start to see these blobs appear. And when you stabilize it and take the exposure, around that star were 2 planets that are sort of out, at Jupiter kind of radii and Jupiter and Neptune kind of brightnesses. And these are 10 to 100 million times fainter than their star. And so this project is considered a technology demonstration. It's to prove that we can do this, so that in our next great observatory, which people are starting to think about, we can go after the Earths that are 1 billion times fainter. Luck and perseverance and bravery for this one, but it's going to be tremendous. Okay, I'm almost done, I promise. Another thing Nancy says is that my career was quite unusual, so my main advice to someone interested in a career similar to my own is to remain open to change and new opportunities. I like to tell students that the jobs I took after my Ph.D. were not in existence only a few years before. I like to tell this to young undergraduates to think about the people who are retiring this year, the year they entered the workforce, and what the technology was then, and the types of jobs people did, and the types of jobs, what the jobs look like now. So one of your best skills to learn is the skill to be flexible and learn, the skill to learn. To put things in perspective, Roman was once called W First. And that mission was kind of put together around this time frame, around 2010. And so my job, working here at the Science Operations Center, was not in existence, was not conceptualized, even 10 or 15 years ago. Just to emphasize that. Science is changing, the jobs do change. So we're way on the other side, and Roman will launch just on the edge of the slide deck over there on the screen. Just to take that point home. Nancy was one of about 25 people that graduated with a Ph.D. in astronomy in 1949, maybe? 49-ish. Today, thousands of people graduate. We have this new facility that we're working on here that's going to require new ideas and new thoughts, and we're already planning for something that will launch in 2030, way off the chart and almost into the other room. And those jobs will look different. So I think I always like to end on a moving forward note, which is those that are listening to think about what those jobs might look like, to always think a little bit further ahead. And just because a skill isn't necessarily directly applicable with what's going on now, it doesn't mean it's not worth thinking about it or investing in it. When Nancy graduated with her Ph.D., there was no such thing as a NASA administrator. It was for astrophysics. It was a job that she created, basically, when she was first hired. And this is my last slide, which is, again, the looking forward, the hopeful part. I never seriously considered any occupation other than astronomy. A piece of artwork I did when I was in 3rd grade shows a girl gazing out the window at the night sky next to a poem about looking at the stars. So again, this comes from the children's book, but it's just to hit home that I think a lot of us scientists, and especially astronomers, we start looking up, we start with this awe and curiosity about the night sky, and don't keep that. I mean, don't not keep it. Keep that. That's where a lot of us start, and eventually you could be the mother of the next Hubble. So thank you very much for listening to Roman Mission. I hope you understand a little bit more.
Thank you. Thank you. Thank you, Rachel. So this is, we have time for some questions. And this is a little bit of an unusual public lecture in that we don't normally have a room full of other scientists. And so Rachel and Joan, you get first crack at any questions, but if they want to punt it to any of you experts out here, any of you scientists or engineers, we have a room full of them. So if we get really hard online questions, this might be a group effort. All right.
They brought their own backup.
Yeah, that's right. Okay, so do we want to start with some online?
Sure. All right, so I'll be bringing the first question from online, which is a little more engineering, but will the telescope have the ability to be upgraded or changed over time? Is it possible to do an over-the-air firmware update? Is there any plan for hardware changes? Is there servicing planned?
Got it into a new mode. Right. So the telescope will be at L2, which is not in orbit around the Earth. It's pretty far away. You can do software changes, sort of. But you can, and it's possible with appropriate robots that you could send a robot out there to swap things out. And maybe you could send a person in a long time. But in general, the mission is 5-year lifetime. Just a reminder, Hubble, I think, was a 10-year or 15-year. It went on for 30 years. So these missions do tend to stay around, but we're only planning for those 5 years right now with the hope that it will stay around for us. So it's possible, but the technology does not exist at the moment that would allow us to do that kind of servicing.
That kind of leads us directly into our next question from online, which is, why do we hear talks of 5-year missions when you have fuel or ability for 20-year missions?
Right. So, you design a mission to meet requirements. And you want it to meet those requirements to 99.999999999% confidence. And it turns out when you are 99.99999% confidence in engineering, you've usually done a really good job, and that thing will surpass its lifetime. So when we talk about JWST fuel, And in particular, this is, I think, probably come up in people's minds around JWST. You know, you think about all the possible things that could happen on its trip from Earth to L2, all the possible ways that it could have to use extra fuel, and you add all that up, and that goes into that 99.9999999% confidence that this mission is going to be successful. So sometimes you end up with extra because you prepared really well, and maybe those things didn't happen. It's also a matter of, you know, money. It's also a matter of having science requirements. The things that we are required to do and that we will try to do can be achieved in that 5-year time frame. You know, it's also practical to think in those kinds of terms. So we do have admins, so hopefully this was who think about this a lot more than I do. But hopefully that's a reasonable answer, but it's often just that you plan something to such a precision that you were 85% confident that you would get 10 years, say. I'm making those numbers up. But we only report what we're 99.9999% confident we're going to be able to do.
All right, we've had an online. Let's take somebody from the audience. Oh, we'd rather hear you, please.
Okay, so this has been fascinating. I thoroughly enjoyed it, and I almost see you as the follow-on of Nancy Grace Roman. So I just wanted to say that publicly. But let's say it's the year 2075. What do you think the capabilities will be then, especially with telescopes, et cetera? If you had unlimited budget, you had people with the right skill set, and all, how would it look in the year 2075? Or maybe that's not a fair question, but
No, it's a good question. There's a tricky thing you can do called interferometry, and that's where you put multiple telescopes together and you combine the light beams from each telescope, and you get the effective telescope resolution of this huge thing. It's used a lot in radio astronomy because the wavelengths are so large that I don't want to say it's easy, it's extremely difficult, but it's much easier than like the light we see to use this technique. There are interferometers on the ground. They're sort of like the size, optical interferometers, they're like the size of a campus, say. The radio interferometers are about the size of the Earth. There's telescopes all over the Earth, and you can combine them together and get an Earth-sized beam. This is what was used to, say, observe the black hole in M87, among other really exciting things. In 2075, I would hope we would be able to have interferometers, maybe an optical, but across the size of like the Earth's orbit, say. That would be cool. That's really hard. That is extremely hard. But you know, if you had to aim for something that would really make the engineers and the data scientists really have to think hard, it would be trying to do something like that. It's borderline impossible. It's definitely impossible now, but it would, yeah. That would be cool, because then you would have effectively a planetary orbit-sized resolution machine, which would be, it's unfathomable. I can't do the numbers off the top of my head. Yeah.
Any other questions in the room?
So just briefly, thank you for talking about the coronagraph capabilities of Roman. This is kind of a little bit of a general question, but how would you compare the sort of capabilities to detect and characterize exoplanets from JWST to Roman? What are kind of the major advances beyond what JWST can do?
Yeah. I know this because someone asked this question in the scientific session. So this is this is a really good question. And so I'm going to say what my colleague Julian said. JWST does not have deformable mirrors. So I showed that step where we adjust the mirror to take into account the intrinsic variation in the light beam. JWST can't do that. That's what got us to that amazing ability to see that contrast ratio. JWST has a coronagraph, one of the instruments does, HST does as well, but they're just doing that part where they take the middle part of the light and send it out to the outside and block it. They're not doing that part where they hyper-stabilize everything and reduce that noise pattern that we were showing. That's the difference. This technology, we have coronagraphs on the ground, but they can't reach that precision either because things are moving. It's very hard to stabilize. So that is, and the atmosphere. But that's the difference, is that it's that deformable mirror, that last step is something that JWST can't do. JWST can do other things. And the really exciting thing is to think about what we learn from the Roman coronagraph community program, this technology demonstration, and how that changes how we look at things with JWST, and then how that influences the next generation that will fly on the habitable worlds. I saw these in the lab at the Jet Propulsion Laboratory, and just walking around the instrument is enough that they can see that in the data that they're taking. Like, this is how precise. They have to position the electronics to picometer, so 1 part in a billion, to make this thing work. And I asked them how they do that, and I was like, lasers, right? And like, yes, lasers, and it would take all afternoon to explain it. Cool. But that's the difference. That it really is on the edge of magic. But it's very believable when you meet the astronomers that do it. Yeah, I trust, I have faith.
Thank you.
All right, we have another question from online, which is, we've talked a lot about ground-based, or at least alluded to ground-based versus orbital telescopes. If you had your choice of anywhere you could position like a station or an observation, where would you put your telescope?
So for some things, the back of the moon seems pretty cool. You're always looking away. There's no light pollution. It's very quiet as well, like radio quiet. So that's where a lot of really interesting things could be done on the back of the moon. The moon dust, because the moon doesn't have an atmosphere, moon dust is quite sharp. So there's a lot of things that you have to figure out how to do. But that would be really cool, because there are things that we just can't do because of how loud everything is here on Earth, both in the radio and in the optical. I really want a fancy space spectrograph that does high resolution. So when I say that, spectrograph, instead of taking light picture in one color, it spreads the colors out. And I would love to have something at high spectral resolution, because that will give you the ability to measure the chemistry of stars. Things now aren't quite high enough resolution. That's the thing that's not on the current menu of options for this next telescope that I would really want to have. As far as where to put it, L2 seems pretty decent, I think. L2 is pretty nice, I think, yeah. Cool.
All right, I'm gonna take the liberty to ask the last question, because I want to turn it around a little bit on you, Joan, because you asked a great question. What would it look like in 2075? I want to turn a little bit around. What do you think Nancy Grace would say to see the capabilities of her telescope, her namesake telescope? And we actually need a mic for you, don't we? Here you go, you can use this.
First of all, she would be so honored. And she's the type of person without, I mean, she's the type who would ask that kind of question in terms of, well, how would it look in 2075? So her thing is, yeah, I can see what it can do today, but I'm also want to start thinking in terms of what it can do tomorrow, and not just tomorrow, but let's go 5 years from now, 10 years from now, 20 years from now, so that we can always be reaching towards something and not become stagnant in the present day. And that would give us an opportunity to learn from that and how to make certain projections. So I think that would be her thing, like, oh, this is great, no, and I feel honored and whatnot. Okay, let's talk about the follow-on, all right? And that way, to be able to inspire other people to be able to participate in that as well. So I think that would be her position.
Great, thank you. Let's thank both of our speakers, Joan and Rachel. And with that, we'll close the public lecture. Thank you all for joining.